Welcome to today's webinar, Using Machine Learning to Optimize the Mixture of an Hydrogen IC Engine. Thank you for joining us today for the 7th installment of the 2024 CONVERGE webinar series. My name is Matthias Sulis and I am part of the business development team at Convergent Science. I will be your host for today's event. It is very exciting to be here with you today and learn from our partner, Volvo Group Trucks Technology, about IC engine modeling and machine learning in Converge. Convergent Science is a rapidly growing computational fluid dynamics software company. Our flagship product, Converge, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. Converge features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our clients. The Volvo Group is one of the world's leading manufacturers of trucks, buses, construction equipment, and marine and industrial engines. Volvo Trucks supplies complete transport solution for discerning professional customer with its full range of medium and heavy-duty trucks. The customer base is provided via a global network of dealers with 2,200 service points in about 130 countries. Volvo trucks are assembled in 12 countries across the globe. In 2023, approximately 145,000 Volvo trucks were delivered worldwide. For nearly a century, Volvo trucks have been innovating for people to make life easier, better, and safer. Volvo Trucks is determined to lead the way towards a sustainable transport industry. Now it is time to introduce our speakers for today's event. Dan Probst is a senior principal engineer at Convergent Science. He has 15 years of experience with engine research and simulation, with particular emphasis on optimization, simplified models, machine learning, and AI. Mukul has been working as a senior research engineer at Convergent Science India for the past 3 years, supporting our customer across India, Southeast Asia, and Australia. He focuses on IC engine validation, consultancy, and research projects on topics including alternative fluid combustion simulations such as hydrogen, methanol, and ethanol. Alen Jose is a specialist simulation engineer at Volvo Group Trucks Technology, Bangalore. Holding a master's degree in automotive engineering, he specializes in thermal and fluid science. With more than 10 years of industry experience, Alen has created and validated various CFD models and other numerical tools to address complex fluid flow and heat transfer challenges. His recent focus involved innovative solutions for modeling hydrogen internal combustion engine, including simulation for heat transfer, prediction, pollutant formation, and exhaust after treatment. During today's webinar, if you have a question for our 3 speakers or the rest of the team at Convergent Science, please use the question box on the GoToWebinar toolbox. Questions submitted during the webinar will be answered at the end. Without any further delay, I will now pass the ball to our speakers. Alen will go first. Thank you all.
Thank you. Thank you so much, Mattia, for the introduction. So here I am showing the brief overview of today's webinar. I'll be talking about the rationale behind the approach and the details about the validation I performed on the Sandia H2ICE engine, followed by Mukul on the design of experiments and HPC runs. Dan will talk about the ML model development, and finally, I will be concluding with the findings. This slide shows Volvo's path to carbon neutrality. And it's our long-term ambition is to have 100% safe, 100% fossil-free, and 100% productive products throughout the globe. And today, my focus would be on the 100% fossil-free aspect, where Volvo believes that to meet the stringent regulations which is coming up after 2040, we need to have multiple solutions to meet different market requirements. Now let's talk about the simulation-driven design. I hope that the flowchart is familiar to many. And one key highlight here is the redesign aspect. This would work easily if you are in a conventional product development. I call it gasoline or diesel engine. It is of course fast, it is cheap, and it's effective. But the bigger limitation here is it's always restricted towards the experience of the designer and the simulation engineer. And here in this particular flow chart, we are going to propose to use machine learning for our analysis or our optimization. So the big question, what is it for ML in simulation? As I said, we have to be competitive considering the lead time to market. Now we are talking about new technologies, not just hydrogen. We are talking about ammonia. We talk about methanol. So this combustion is new, though the engine is the same. The combustion is new in all these fuels. And with new technology, this poses a challenge as the unknowns are more. So in order to have a better understanding, we need to auto-generate as much as designs as possible. And of course, our intention is not to replace simulations, but rather to have optimization design in product development just by replacing the redesign or the iteration aspect. That's the whole idea of doing such an activity. Now coming to the objectives. First, we need to validate the engine image data in the form of velocity, that is PIV, and H2 mole fraction, that is in the form of PILF, using simulations. The next aspect would be we need to identify what are the parameters that affects the mixing. Considering the dispersion and diffusion of hydrogen in picture, we need to come up with computationally efficient simulations without compromising much on accuracy. I know that's not, those two terms will not go hand in hand, but that is something which we are trying to address here. And finally, we need to find out how machine learning can be used to maximize the mixing. So let's talk about the baseline validation. So we are considering the Sandia H2ICE engine data, which is published in the Sandia website. And this is of course a no combustion case that operates at 1500 RPM, roughly about 0.5 liter capacity. And this is the experimental arrangement on the right side where you can see a tumble plate to enhance the tumbling motion within the cylinder. And this slide shows how my injection parameters are considered for the present study. One thing to note here is that the lambda under consideration is roughly about 3.77. And on the right side, you can see the injection profile. I know it is not very realistic, but our intention is to replicate the experiments. So the experiments were carried out with the exact same injection rate shape. And finally, at the bottom, you can see the injector geometry used for this present study. There is one interesting parameter we need to consider here. The injection pressure for this DI system is roughly about 100 bar. So we have used the CAD information available in the Sandia website. And this study, what we are showcasing today, will consider a case with injection and tumble plate. The reason why I mentioned this because there are many other cases that is published in the website. So we are only considering the extreme scenario where we consider tumble plate and injection. And here you can see that the pressure and the temperature boundary conditions along with the valve lift. One thing to note here is that Sandia's original experiment is with nitrogen as the bulk gas. But the present study is with air after comparison with the flow field from experiment. Another advantage of this approach is the model can be easily adapted for combustion simulations. So if you ask me if there is any difference, and considering air instead of nitrogen is the only difference in the present work. Okay, let's talk about the results. This particular slide shows the PIV data for velocity starting from minus 120 crank angle all the way to minus 55 crank angle. A varying scale is used to represent the velocity field for the crank angles shown in the slide. And to be honest with you, we have got a good correlation between experiment and simulation. However, if you want to look deeper into it, as observed by many researchers, the width of the cone is narrower at minus 120 crank angle compared to the experiment. And this is due to the measurement, uncertainties, and approach, as the bulk gas is only seeded in case of experiment. So what happens when you inject hydrogen? It takes its own time to align or to predict the velocities corresponding to both hydrogen and the bulk gas. So coming to the mole fraction of hydrogen. Okay, sorry. Before going there, you can also see that from minus 100 to minus 70 crank angle, there is a difference in the velocity between experiment and simulation. This is because of the lesser dispersion offered in simulation, and it is mainly due to the turbulence model what we are using. That is nothing but the RANS turbulence model. And here it clearly shows that RANS turbulence model is not able to resolve the length scales. So the obvious solution to this problem is to use LES and DNS. But considering the runtime and the predictions for velocity, we were satisfied with the predictions from RANS. So we decided to continue our studies with the RANS. And this slide shows the variation of hydrogen mole fraction. And as I explained in the previous slide, the crank angle varies from minus 120 to minus 55, where here also we use a variable scale to represent the jet of hydrogen. We can see good agreement in jet penetration even after strong wall interactions. But as the crank angle progresses, you can see differences between experiments and simulation. And here again, we, we, we believe that the differences are due to the measurement uncertainties. And as the jet reaches at the top dead center, the differences in hydrogen and air mixing is more apparent. Again, the turbulence model is to be blamed here as well. That being said, despite of the obvious limitations, considering the runtime as a factor and the predictions what we have made so far, we decided to go ahead with the RAN simulation. Okay, so how we were able to validate the model. So we have used inlaid mesh, velocity AMR, and boundary embedding to resolve the flow which is coming out of the injector. And these are the best settings for predictions along with the careful selection of solver settings. But the downtime or the downside here is it roughly takes about 120 hours to complete a simulation from intake valve opening to top dead center, not even combustion. And if you are talking about doing optimization on this particular case, it won't be computationally feasible. So we came up with another clever idea by coarsening the mesh. So as we move from left to right, the mesh has been considerably coarsened. And we expect some numerical diffusion considering the fact that we are coarsening the mesh, but we also wanted to see how it is going to affect the bulk flow properties. This slide shows how my 2D results are varying for all the 4 conditions which I've shown in the previous slide. As you can see, the in-cylinder pressure and the in-cylinder trap mass is not being largely affected, whereas there is some impact on tumble and the turbulent kinetic energy. But as it reaches closer to the top dead center, the values are being identical for both tumble and turbulent kinetic energy. And this variation for tumble and turbulent kinetic energy is expected because we are not resolving the velocity properly. On the other side, one interesting finding here, which is now apparent for all the gaseous injection system, is that the bulk flow after the injection is controlled by the injection parameters. So essentially what it means that the tumble is generated through injection, which is an important finding here when we were doing this work. With that in mind, what we have done here is we are comparing how our results are varying if I am using the most finer settings to the coarser settings. And it's apparent that we are losing the details here, but considering the benefit what we are getting with respect to runtime, roughly about 20 times, we decided to go with the base 4mm with AMR only settings. So no inlaid mesh, no boundary embedding, anything. We are just going to resolve the flow using base 4mm and AMR. So now, in order to talk about the design of experiment and machine learning, I would like to invite Mukul to continue with the webinar. Thank you. Over to you, Mukul.
Thanks, Alan, for that explanation about the validation of the base case. So before explaining the DOE, let me quickly, I think, just reiterate three parameters which Alan just mentioned. So this is how the base case looks like. If you can see my cursor here, that's the intake port, and we have a tumble plate here, which, let's say if air flows from here, it is supposed to create a tumble like this. At the center, you can see an injector, and I have just zoomed its view on the right hand side. This is how the injector looks like. Now this injector is inclined with vertical axis, which I will be calling umbrella angle in this particular exercise. If you look at from the top view, in the base case it's horizontal, but even that angle can vary, which I will be calling azimuthal angle. And the injection, the hydrogen will be injected at some pressure from here. The boundary condition will be given at this wall, or this boundary, sorry, this inflow. And that will be my third variable. So going to the next slide, for my design of experiments, I will be having three variables: the azimuthal angle, which we will be varying from 0 to 270, umbrella angle, this angle, which we will be varying from 25 degrees to 60, and the injection pressure. Like here, the H2 will be injected at different pressure, and the range will be between 20 to 80 bar. So if you see, I have three input variables, and all three input variables have their respective ranges. Now we will vary these three different parameters, but what exactly we'll be checking? We will be checking these three parameters. One is the uniformity index. The mathematical formula is given here. Basically, it represents mixing, like how uniformly the fuel and air, or in this case, hydrogen and air, is mixed in the cylindrical chamber. So it varies from 0 to 1. 1 shows it's very well mixed, and 0 it's like a very poor mixing. So that's the first parameter. Second is max tumble y. Now y-axis is a perpendicular to the screen. So if you see, currently the tumble is like this, and as Alan has explained in his in the validation, when hydrogen is injected, it itself creates a tumble, and which kind of dominates the tumble created by the air. And turbulent kinetic energy at TDC, when the piston reaches TDC, generally our spark is either is at TDC or like before TD, like some like inclined angle before TDC. So we will be measuring these three parameters uh, as a like output for my design of experiments, which will be fed to my AI/ML model. Now, obviously, that when we have these three parameters, we will be trying to maximize them. So in such a case, what we do is we try to get like minimize the merit function. So merit function looks something like this. where the respective first values are relative, like are the maximum values which these variables can attain, and 0.95 divided by uniformity index, 2.3 divided by tumble y, and 11 by tke. Like this is a kind of a merit function what we gonna use when I'm gonna use a machine learning model on my DOE. Okay, so if you can see on screen, like this distribution, you can see two images here. Now this is my entire DOE. On the x-axis here you can see umbrella angle, on the y-axis azimuthal angle, and on the right-hand side you can see azimuthal angle or pressure versus azimuthal angle. So basically, as I have explained before, we have three input variables and respective ranges, but we need to distribute our simulations over the ranges uniformly, and that's something what we do using a statistical method, Latin hypercube sampling. So these are our total number of cases. So to give you like one precise example, if you see this red circle, now this is, if you can see here that umbrella angle is kind of between 25 to 30, azimuthal angle is near to 50, and pressure is close to 20. And to be precise, the same point I'm just representing it by this case setup where we actually change our geometry by choosing the three variables. As I said, umbrella angle is 27. I changed this point. Azimuthal angle is 48. So if you see in the top view with respect to horizontal axis as well, the injector direction has changed. And in this particular case, I am injecting the hydrogen at 21 bar. So summarizing it again, input variables are three: umbrella angle, azimuthal angle, and injection pressure. Output variables are also three: uniformity index, tumble y, and tke. And we have DOE of cases like spread across the range of input variables, and we're gonna measure these three values. So our entire DOE, which consists of 132 cases, which I just explained on the previous slides, we ran all of these cases on the Converge Horizon platform. What exactly is that? So we partnered with Oracle Cloud Infrastructure uh, to create a flexible, affordable cloud platform for Converge users, and you can run a number of simulations here parallelly in a very fast and secure environment. So if you're a Converge user, you can have your own license. You can bring your own license and run it on our cloud, or even directly on Horizon. If you can host a Converge license. So in this particular project, the DOE, the design of experiment, consists of 132 simulations, and approximately, as Alan mentioned, one simulation takes approximately 6 hours. Now, all simulations can be run parallelly on Horizon. So if you talk theoretically, the entire DOE can be completed in 6 hours. Now, here I would like to just reiterate the power of like here cloud computing here, that all the 132 simulations like theoretically can be completed in 6 hours. But in our particular case, we completed in 5 days because we wanted to consciously monitor our results in between. Okay. So this is the important benefit of AIML models over the other optimizers where sequential simulations are required. For example, like now I am going to generate a data. I'm going to generate a result of my 132 simulations, let's say in either in 1 day, or let's say, to be very precise, or considering the practical limitations, in 3 to 4 days. And in 3 to 4 days, I can give all this data to AIML model. And that's the benefit I'm talking about when we compare it with sequential optimizers, because in sequential optimizers, your simulation depends on the previous run. And if you want to run 132 simulations sequentially, it's obviously going to take a week or even a month for that matter. But here, the entire DOE, if we have a access to cloud computing platform, and you can run the entire DOE in just like a couple of days. So yeah, feel free to visit this site, Converge Horizon, if you want to know more about it. Also feel free to contact us. Now this is just a sample screenshot. Like for example, for this particular case, we ran like multiple simulations. I'm just showing 14 here for now. We ran this all simulations parallelly, and you can run all these simulations. See the on the fly. You can see runtime, monitor simulations, see the cost, how much it is costing. You can see it on the fly. Now, all this data, what we generate so quickly in a couple of days, we feed it to machine learning model. And this will be the next part of our webinar, and I would request Dan Probst to take over after this.
All right, thanks, Mukul. So now for the next part of the webinar this morning, I'm just going to show a preview of this machine learning tool in CONVERGE Studio that we've been developing. So for the work last year that was in the paper, we used some standalone tools, but now we've been working on implementing this into Studio. So right now I have our baseline case opened, and you can see this is the same engine geometry that Alen has shown. And so now what we're going to do is open this tool to create this workflow for the machine learning optimization. So we start in the first panel to generate cases. And in this panel, we can create the variables that we're going to use to vary in our DOE. So in this case, we had pressure, azimuth angle, and umbrella angle. And in this case, these parameters are not directly parameters in the converge case setup that we're going to be varying. Now, if we were trying to do a parameter that was directly in the converge setup, we could use a variable from this predefined list, which actually go into the case setup of the converge case. But for this case, as we described earlier, we're using these three variables that then, through a Studio script, set up each case. So in this case, now for these parameters, the pressure, I'm going to put in the min and the max that we decided to vary these in the DOE. And then move over to the design of experiments, where we're going to create the design of experiments. So you can pick a number of runs and then generate cases here. And this uses a Latin hypercube strategy to sample your design space between the min and the max for the variables that you've specified. Once this DOE is created, then you can select a directory and export all of these cases. So what you're seeing now is the run folder is all being created for every one of these cases with the different values of our parameters. If these were in the case setup, they would be directly changed in each folder. In the case of this setup, we're actually using the Studio scripting, like I said. So this takes a minute just to write the files. But then once all the file folders are created, these could be zipped up and put up onto Horizon to run them, or they could be run with a script locally. So at this point in the workflow, you would pause, run all the cases, and then we come back and collect the results. Now, in the case of this study today, we actually already have a DOE that we generated. So we're going to copy and paste this DOE in, because it's really important that you have the same, obviously, DOE for your input features as your results. So now we've loaded that DOE, and we move on to the next step, which is to bring in our variables, which we're here calling our responses. These are our results. And as Alen and Mukul described, we have three variables: a uniformity index, the max tumble, and TKE at TDC. So we're just going to rename these quickly to the variable names. And then we can load in our results. In this case, I'm just going to copy and paste them in. And getting these results from Converge is pretty straightforward. Sometimes we'll write a UDF to calculate some variables that are written at the end of the run. In this case, these could be grabbed from the standard .out files pretty easily using some scripting. And then we just get them in a file and we can copy and paste them in here. So now our results are put in here. We're going to use an optimizer that looks at a merit function. So in this case, we define a merit as Mukul showed earlier in the slide. So we have 3 variables to choose from. We're going to include all 3 in our merit function. In this case, we wanted all of our variables to be maximized. So we want the max tumble to be maximized, the TKE and the uniformity index to be maximized. And then using these same scaling values that we showed from the paper, we complete our merit functions. So these are all what we call performance variables. We're trying to maximize them. We don't have any constraints. A typical constraint may be like a emission. You may like have a constraint on the maximum NOx or something like that. But in this case, we're only trying to maximize our 3 variables. So now we have our input features, our responses, and our merit function defined. So we can go on to define the model that we want to train. So we're training a machine learning model to emulate our CFD data, and then we can run the optimizer on that machine learning emulator. So in the model configuration, this comes up with default recommended settings that are pretty good for a standard case like this. The kind of machine learning model we're using is called a super learner or a meta model, where we have a number of base models. Each response is trained separately, and we can define separate machine learning models for each one. In this case, we just have our default where we're using all 5 available base models. We have a regression model, a random forest, an extreme gradient boosting model, support vector machine, and a neural network. And then once all of these base models are trained and evaluated for their error in predicting our CFD data, they are combined with a meta model to maximize your accuracy. And then ultimately we have a single machine learning model to emulate the CFD for each of the 3 variables, and then we calculate the merit from those predicted variables. So I'm just going to stick with those defaults. It's not the exact same settings as the paper, but they're pretty good. I just need to define a directory where I'm going to export the machine learning model, because when we train the model, we save it at the end as a saved model. So it's basically like a reduced order model. This like I said, this isn't exactly the same as the paper, but it's a pretty accurate model, but also does not take too long to train. We can increase the complexity of the machine learning model, but in this case, we actually get pretty good accuracy with just this basic fast model. So we can look at both our training data set and our test data set. In this portion of the workflow, we're making sure our machine learning model is accurate enough, or is a good emulator for the CFD data. So we're reserving 10% of our test data runs for testing. So that means we didn't use them to train the machine learning at all. So typically your training data will match very well. As you can see here in these plots, we're showing the CFD max tumble on the x-axis, and then the predicted max tumble from the machine learning model on the y-axis. If this is a perfectly accurate emulator or machine learning model, all the data points will fall right on a one-to-one line. In this case, there's a little variation just because of the base models we're using. But much more importantly, our reserved test data fraction is also falling along that one-to-one line fairly well. And that's telling us that this machine learning model does a good job of predicting data it hasn't seen before. And that's what's important in order to use this machine learning model for optimization. So like I said, we're using a meta model. So what that means is that we combine our 5 base machine learning models with a single meta model to get the most accurate representation. And these weights show you which models are used the most in our final result. So in this case, the gradient boosting and the support vector machine are used the most, and you can see their cross-validation root mean square error is the lowest. If we switch over to TKE, it's a similar story, but random forest is being used there also. And then for the uniformity index, we are using the neural network the most. So by using this sort of automated meta model superlearner strategy, we get a pretty good fit for all 3 of these variables, and we end up using sort of different configured machine learning models. Now at this point, we could go back and look at some of the hyperparameters for our machine learning models and even maybe increase or adjust the parameters for them to change the complexity or the regulation of them or other things like that. But in this case, like I said, our accuracy is pretty good and we have a pretty fast model. So I don't really feel like we have to do that at this point. But all the parameters to these base models are available if you go into the settings for each model. So at this point in the workflow, we're ready to go on to the optimization, but I'm just going to retrain the model with the testing turned off first. And the reason I want to do that is because we like the settings for the machine learning models. We like the accuracy of the machine learning models. But for the optimization, we want to train on all of our data. So we're going to train on 100% of the data, save our machine learning model. In this case, you see that the test data disappeared. I can go back and look at the training data, but that isn't terribly important to us. You know, there's one thing I forgot to mention, and I'm just going to go here and do this quick, is I forgot to show the merit. So I'm just going to train this quick with the test fraction again and show that merit, because that's ultimately what we're going to be optimizing on. So here I've retrained on the with the test data withheld, and I'm just going to show the merit. So we take those 3 predicted variables and we calculate our merit. And now this is showing our 10% test data for the predicted merit function. And this is ultimately what's really important for optimization, is that we do a good job of predicting the merit for each data point. And you can see it falls pretty well along that one-to-one line. In this case, we're trying to maximize our merit because that will maximize all 3 of those underlying variables. And you can see that we have good accuracy with some points out there with the maximum merit. All right. So now I'll just come back and turn off the test fraction, train this one more time, and then we'll go over into the optimization step. Okay, so now we have our optimization panel. So we automatically populate our 3 variables. We by default put in the min and the max values of the DOE for our optimization ranges. So this is saying we're going to try to optimize this design space within these min and max values that we originally ran the DOE. Now we don't let this go beyond the min and the max, because with a machine learning model, if you go outside the data where it's been trained, you will really get garbage results. So you want to stay within the definition of the DOE, but you could restrict this further if you wanted to during the optimization. In some cases, that may help you optimize the search space a little better. But in this case, we're just going to leave them to the full extent of the DOE and hit optimize. And now we run an optimizer on the machine learning model. And you can see with, I think we ran a bunch of evaluations and got to the point where the tolerances was reached, and we are predicting now an optimum of our machine learning emulator. And you can see on this plot now we're showing all of our original DOE points in the black circles, as well as our predicted optimum in the red cross. So that optimum is predicted to happen with a pressure of 63, a azimuth angle of 181, and an umbrella angle of a little over 41. And this is showing the optimized merit function. Now, if we go to each of the individual variables, we also have a predicted max tumble. You can see where it falls versus azimuth angle. You can see where it falls versus pressure. We can also look at the uniformity index. Now, this is one interesting thing. Here, our optimum uniformity index against pressure is lower than some of the other DOE points, but that's because we're optimizing all three of these output responses at a single setting for all three of our input features. So the uniformity may not be higher than all the DOE cases, and some of these other, like TKE, may not be higher than a couple of the other DOE points. But overall, our optimum is predicted to be better than any of the DOE points. So now at this point, we want to confirm this with CFD so we can export an optimal case setup using these three values of pressure, azimuth, and umbrella angle. We can hit this button, create a run folder, upload that to Horizon, run it, extract our CFD predictions for our responses, our uniformity, TKE, and tumble, and then see if that actually is an optimum. In some cases, you may want to do this, iterate this a few times. So in that case, you could take this predicted optimum, tag it on at the end of your DOE, take the result for those three responses for that case and tag it on here, and then retrain a model with that added data point and re-optimize it. And what that would do is it would take that predicted optimum, refine your search space in that really important area and retrain a model, and perhaps iterate a few times to get a slightly better optimum as you're narrowing it down in that very close area to the global optimum. So with that, I finished this walkthrough of this tool we've been developing, and I'm going to hand it back to Alen for the conclusions.
Thank you, Dan, for the excellent demonstration. So continuing from what Dan has mentioned, I'm showing here the results, what we did through optimization. I'm only showing for the merit function. Maybe you will see the values be a little different here and there because it has been evolving over a period of time. And when we published this was the value. That being said, this is something really interesting. So as I mentioned earlier, the Sandia case had an injection pressure of 100 bar. So if if you expect that the injection can create the tumble, then naturally it is expected to have the best mixing with a higher injection pressure. Whereas when we did optimization, what we found out was instead of getting the best mixing at 100 bar, we are getting roughly about 60-65 bar respectively, which is why such studies are important when we are developing something new rather than trying with iterations. So the graph what shows here is that how our merit function is being compared with our baseline data and the iterations or the combination what ML model has suggested. We ran the model again in Converge, fed back this data again into our ML model, and then finally we got an optimized one, which is pretty close here because we had more data available. And that's the reason why from baseline to iteration one, we don't see a huge jump, but it is always within that ballpark figure of roughly about 60 to 65 crank angle and from 175 to 180 degree for azimuthal. And the umbrella angle is roughly about 42 to 44 degrees. So now and here the graph shows what were our base values and what are the optimized values. You can see a clear improvement in tumble and TKE along with marginal improvements in UI, which we did through machine learning. So we are proving a point that if we are using this approach with a cloud-based and a DOE environment, then definitely you can optimize this injection related parameters. For example, now for hydrogen, the cap design is something really critical. And if you're not sure on what approach that you should take, like single hole, multi-hole, or what could be the shape, what could be the volume of the cap, you can use this approach here. And that is going to benefit you because the more the data that you generate systematically, then more the data you have it for your machine learning model and then for optimization. Now, just to show a, a reason why we were able to get the best mixing when we were using a combination of 180 azimuthal angle and roughly about an injection pressure of 60 degree. So the Sandia baseline case had an intake flow which is happening as shown in this picture here, which is against the injection direction. So what essentially the optimization did to have the intake and the injection in a similar direction. And this is a big learning for me because now when we are looking at the actual H2 systems for hydrogen systems for Volvo, we are using this learning to design and position our hydrogen injectors. Then finally, the conclusions. So we found out that the dominant charge motion is through injection, which is fairly important in this case here because of hydrogen. And then we did an rapid optimization. So we validated the model, make the model to run faster, and then we made an optimization within 5 days. So the conventional approach to improve in-cylinder motion involves modifying the design of an intake port. But here, since the injection generates the charge motion, we concentrated fairly on the injection aspect of it. And if we are using the ML based optimization, it has a significant advantage as it allows for concurrent generation of data for all the data points within a day or two by utilizing a cloud-based HPC. This directly speeds up the virtual development process substantially, and it can overall bring down the development time. So as I mentioned earlier, we can realize the optimization design philosophy much faster in this. Now assume that if you don't have an HPC environment, no problem. What you should do, you should start with lesser number of data set. Here we have started with 132 cases, but what you should do, maybe start with 20 cases, train the ML model, bring back the predictions, run converge simulations. Maybe after doing a couple of iterations, I am sure that you will be able to reach the optimum number. So finally, what is the way forward? We already did optimization for multi-hole injectors as well, and we would be publishing this information soon. Then the next step is to do a combustion on the same engine where we will be using a similar approach to optimize the spark position. And finally, it's our wish that we will be using this methodology for Volvo specific H2ICE engine for optimization. Since this method showing a huge potential in saving your time for optimization, this can definitely help Volvo as a group in running simulation or getting results faster to get an optimum design. And finally, of course, once we do it with an actual engine data, we need to correlate this approach how we are predicting. That is another task in pipeline. And one important aspect of this is it is not just restricted to a CFD calculation. You can use a similar approach. As you can see, Dan has copied an Excel sheet. So you can do a similar optimization from 1D data, FEA data, or even engine calibration, which is much more flexible compared to the conventional optimization tools available. And finally, I wanted to conclude by saying this. AI tools, whatever be it, it gives you superpower, provided that you know your domain. If you don't, then there is no point in using these AI tools. We have published all this information in our paper, so you can check this out. And if there are further questions, or if there are questions about today's session, I'm more than happy to answer. Thank you for listening. Thank you so much.